Welcome back. This is the Math Scientist, and today we'll be covering RSA encryption for cybersecurity. First, let's look into what the RSA encryption is all about before we get into how it works. RSA encryption is an asymmetric encryption system where the public and private keys are different, and nobody can access your private key. Only your private key can decode the encrypted message. And if the message is intercepted, it will be encrypted unless the attacker has access to your private key. So if Alice wants to send a message to Bob, it will be encrypted so that little Timmy can't intercept it and read what you have to say. So now let's look into the mathematical background of what goes into the RSA encryption system. There's three main things we have to know: prime factorization, Euler's totient function, and modular arithmetic. Prime factorization is quite simple. It's the process of breaking down any composite number into multiples of prime numbers. So on the right-hand side, if we look at the diagram, if you want to break down the number 48 into prime numbers that you can multiply back into 48, then it would be 2 times 2 times 2 times 3 times 2, and that would make 48. And so you can take any number and factorize it into its primes, and that's basically the essence of prime factorization. The next thing we need to know is Euler's totient function, and follow me on this one because if you don't know it, then it's a pretty key concept that's going to keep coming back in discrete math and cybersecurity. In order to understand Euler's totient function, we need to know what coprime numbers are. Coprime numbers are numbers that are relatively prime to a particular number, which means that the numbers cannot share a common factor. So if we want to find numbers coprime to 9, the numbers 1, 2, 4, 5, 7, and 8 are coprime. The numbers 3, 6, and 9 are not listed because they all share a common factor of 3. So if we want to find numbers coprime to 10, it would be 1, 3, 7, and 9, which means that all the even numbers are eliminated because they all share a common factor of 2 with 10. And the number 5 is also eliminated because it's a factor of 10. There are 4 numbers coprime to 10. But what if I don't want to list these out every time? Then I need to figure out a function which I can plug these numbers into so that it's easier for me to figure out how many numbers are coprime to a particular number. And so step 1 to doing that is finding the prime factorization of the number. So if we take 10, for example, the prime factorization of that is 5 and 2, and that makes 10. The next step is to plug it into this formula. Phi of n is equal to p minus 1 times q minus 1. And so if you plug our number 10 into this and their prime factorizations 5 and 2, it would become phi of 10 is equal to 5 minus 1 times 2 minus 1, which is equal to 4 times 1, which is equal to 4. And if we look on top, we can see that 1, 3, 7, 9, 4 numbers are coprime to 10. Next thing we need to know is modular arithmetic. This is pretty much a very simple concept of how to find a remainder. If we want to look at how this is done visually, let's say we're doing 7 mod 3, which means how many times can 3 go into 7 before we can find a remainder. If we do 7 minus 3, we get 4. So that's 4. That becomes 4 mod 3. So these are congruent to each other. But now we can remove another 3 from 4. And that gives us 1. And 1 modulus 3 is also congruent to 7 modulus 3 and 4 modulus 3. But we cannot remove another 3 from 1, which means that 1 is the remainder here. And that goes for all the other examples we're going to do, where 47 modulus 20, you can remove 20 from it 2 times, and then you can get a remainder of 7. And if you do 6 modulus 3, you can remove 3 twice evenly, and you get a remainder of 0. So that's pretty much how it works. So now let's look at the RSA encryption in action before we get into how it works. So we have a public key 514, 5 being the encryption key, and you're being sent a message M, which has the value of letter B, the numerical value of it being 2. In the encryption process, we have to follow this formula, M to the E mod n. M is our value 2, and E, our encryption key, is 5. Which is the first element of our public key. If we plug that into the formula, 2 to the 5 mod 14, n being 14, the second value of the public key, then we get a remainder of 4. And that's going to be our encrypted message. Our message B, encrypted, looks like the message D, which has a value of 4. But now you want to decipher this. You receive a ciphertext, but you have to decrypt it now. The ciphertext D has to be thrown into the formula C to the D mod n, where C is the value of your ciphertext 4. D is the decryption key 11, the first value of the private key, and modulus 14, the second value of the private key. So 4 to the 11 mod 14 gives us a giant number mod 14, which yields 2 modulus 14. So the remainder in this is 2, which is the value of our original message, B. So how does this work? Why did these values work so well together? There's a math behind it, so let's look into that. There's 5 simple steps to RSA encryption, and we're going to go through them one by one. So first thing we do is pick 2 prime numbers. In this case, 2 and 7 are the prime numbers for this example. Usually, in an actual RSA encryption, they're like hundreds of digits long, these prime numbers. And so it's really hard to determine which 2 prime numbers are in action, and that's why it's so difficult to break. Now we have to determine n, which is p times q, the 2 prime numbers multiplied. And so that gives us 14. And now we have to determine phi of n. Our p is 2, our q is 7, so 2 minus 1 is 1, 7 minus 1 is 6, and so our phi of n is 1 times 6, which is 6. And at the bottom, we have a little visual representation of how that's determined. 14 is an even number. So we can eliminate all even numbers before it, and that leaves us with just 1, 3, 5, 7, 9, 11, 13. But 7 is also a factor of 14, so we can get rid of that. And that leaves us with 6 numbers written in bold, which are 1, 3, 5, 9, 11, 13. And now that we have phi of n, let's determine the encryption key. There's 2 factors that go into this. The encryption key has to be greater than 1 and less than phi of n. So I've listed numbers that are greater than 1 and less than 6 in our case. So that's 2, 3, 4, and 5. Now from these numbers, we need to find a number that's co-prime with n and phi of n. Our n is 14. So we have to eliminate any even number that would share a factor with it. And our phi of n is 6, which means that 3 is a factor of 6, so we have to get rid of that. And that leaves us with the number 5, which is our encryption key. Now that we have our encryption key, let's determine the decryption key. The formula to find the decryption key is the decryption key times the value of the encryption key modulus phi of n should equal 1. So we have to get a remainder of 1. Now we know our encryption key's value is 5. So 5d modulus phi of n, which is 6, has to equal 1. So let's look at the little chart below and see which value is fitting for d. So we need to find something with a remainder of 1, and we know that these can get us a remainder of 1 after being plugged into the formula. So we can choose either 5 or 11 as our decryption key because we have to end up with a remainder of 1, and so we can choose the number 11 and that'll be our decryption key. Once that's done, we've finished the whole process, and our n is 14, which is the product of our 2 prime numbers, and then phi of n is the number of co-prime numbers to our product of the prime numbers. That will give us the encryption key from which we can make our public key, and then with the encryption key we can find the decryption key, which would give us the private key. And that's pretty much how the whole RSA encryption system works in a simplified manner. If you're interested in reading into this in more detail, I've put a link in the description to a paper that explains this really well. Thanks for watching.